All right, so at this point, you have learned a couple characterization techniques. So we have IR, right, that tell you about functional group, mass spec, which tell you about the mass of the compound, and you can convert to a molecular formula and stuff. Degree of unsaturation can help as well. Now we're going to move on to a more powerful structural characterization techniques we call carbon NMR. Okay. All right, let's be familiar with the carbon NMR real quick. So the carbon NMR spectrum will look something like this. You're gonna see a carbon NMR signal, so like a peak come up, look like this. All right, and also a chemical shift, which is uh, shows from 0 to over 200. Okay, the unit is ppm parts per million, but we'll get there later. Okay, all right. So this is carbon NMR. Now there are two information in the carbon NMR spectrum. Okay, I have two main information that we're gonna look into it. The number one is the number of signal, which is the number of chemically non-equivalent carbons. Basically, the number of different carbons. For example, right here, if you look at this molecule is a solvent called ethyl acetate. Okay, so there are four different carbons. Okay, so technical term is for chemically non-equivalent carbons. So these are four different carbons. So we have carbon 1, show up like on this peak right here, carbon 2, 3, and 4. This is simple. Okay, so four different carbons, and I show different like right here. All right, let's do this. I'll give you cyclopentane. Okay, first off, how many different carbons are there in this molecule? Well, you should realize that this guy have the same, all five carbons are the same, right? So if all five carbons are the same, well, only one signal. Here we go, right? That's simple. All right, try this one. Watch out for symmetry. Pause the video and let's count number of carbon. Okay. All right. Once you get that, let's count with me. So we have 1, 2. Yeah, there's symmetry right here. So 1 and 2. These are four symmetry. Okay. So four carbon are the same thing. 1, 2, 3, and 4. So there are four different carbons in these molecules. So you should expect four signals. All right. You should expect four signals on this carbon. Excuse me. I wrote right here resolve into two signal. It means that sometimes the location, which we'll talk about it later, we call chemical shift. If the location of signals are too close, I mean they kind of like they get really close, we can't really see. But if you really zoom in or use a higher magnet, the NMR instrument, these two signal will separate, and you can actually see it. Okay, basically, so we have 1, 2, 3, and then 4. But there are two signals in here. I can't really see in here. All right. All right. Try this one. So this guy. So I'm adding OH. All right. Go back right here. So from this compound, so I'm adding OH onto that carbon. Lost the symmetry. Okay. Lost symmetry. Let's count number of carbons in here. Pause the video first. Let's count by yourself and then check with me. Okay. All right. So all carbons are different now. There's no symmetry in here. So maybe we're gonna go 1, 2, 3, 4, 5, 6, 7, 8. Well, I'm running out of the color, so I'm just number now. 8, 9, 10, 11, 12, 13. So you expect 14. I forgot 14 right there too. All right. So you expect 14 peaks on here. You can count it. I'm not counting it too many. So try one more time. Okay. All right. Once you've done that, try to do it first. Do by yourself first before you check with me. Okay. Let's say I'm gonna go 1, 2, 3, 4, 5, and 6, 7. These two are different. Some of you are like, what the heck? They're different in here. The only reason is, take a look here. So when you have a double bond, this bond cannot rotate freely. All right. So these two are different in the sense that, all right, I'm gonna use the blue carbon right here as a reference point. Okay. All right. The light blue or the cyan carbon is closer or cis to the blue carbon, and the purple are trans or further away, right? So when these two carbon are in a different environment, that's what we call chemically non-equivalent. They are different carbon. So be careful, okay? And you can count on here. So 1, 2, 3, 4, 5, 6, 7. So there's 7 signals, okay? Oh, by the way, so we have the signal at 0 ppm, okay? That's tetramethylsilane. We use that as a reference point. And all the peaks right here, all the signals are based off TMS. Okay, the TMS look like this. Here we go. All right. So TMS have the um, I lost a little chemical shift. Chemical shift at zero. Everything else based off this this peak. Okay. All right. Let's talk about chemical shift.